Okay, we're going to continue on here. Chapter 13, equilibrium. So last time we got into equilibrium calculations from initial sort of calculations. We talked about a couple important things, including Q. Q is the reaction quotient. It is used a lot of times to figure out a couple of things. And it's calculated, by the way, the exact same way as you would do your equilibrium constant. So products over reactants. You also, just like you would do with K, you would also take the coefficients as the exponents when you do so. Again, only aqueous and gas would go in there. So pretty identical calculation as you do with K. The difference is we're trying to find out really in a sort of straight sort of Q type problem whether or not the reaction's at equilibrium. And if it's not at equilibrium, which way it needs to proceed to reach equilibrium. So remember that if Q is less than K, it's not at equilibrium. It needs to go opposite of where that's pointing. So it needs to go to the product side there or to the right, basically, to make more products to reach equilibrium. If you calculate Q and it does equal the K value, then you are at equilibrium. Doesn't need to go anyway in that case. Q is greater than K, is not at equilibrium, and again, going opposite of sort of where this guy is pointing, will be where it needs to go. It needs to go towards the reactant side or to the left in this case. So we use K, or we use Q when we are given pretty much all of the concentrations, and that would obviously is the only way you would be able to calculate Q. So obviously, if you're not given everybody's concentrations in a problem, you can't calculate Q. The second place where we see Q is sort of in equilibrium calculations. Again, if you are given sort of the starting amounts of everybody, you should calculate Q to make sure that you're not at equilibrium, which if it's an equilibrium problem, you most likely will not be at equilibrium, but it may also affect the change part of that calculation in terms of which way it's going. So that will help you sort of decide. Speaking of that, we talked about equilibrium calculations, and basically we use, again, our ice tables to do that. Initial, change, and equilibrium. And we basically, when we have an equation, I'll learn the alphabet one of these days. There we go. I'll go that way. So say we had 2 molar of this guy, we got 4 molar of this guy, and we got nothing of this guy. So remember that the change part is really kind of the most important part of this table in a sense. It takes into account both the stoichiometry and it's also what you're really trying to find. So with that being said, we do need to take in those coefficients when we do this part. So we got to make sure that we have the 2 there. That takes care of the mole-to-mole relationship. So all the stoichiometry is correct. Same thing here. These would be minuses as well, because in this case, since we have no products to start with, we could assume that the forward direction in this reaction would take place. And obviously, we would be making our products in this case. This all just gets carried down. And what we do is we go into our equilibrium expression. And in my bad made up example here, cry at all the math you would probably have to do in this one. But we basically put all this stuff into this guy. And obviously here, the goal would be to solve for X. And once we solve for X, that will be all the X's here, pretty much in the equilibrium line and also the change line. And that will allow you to calculate the equilibrium concentrations of everybody. You could do this with concentrations. You could also do this with pressures. Again, if it's an ice table and you're doing a calculation, in terms of pressures, it should be an atmosphere. So that should be the pressures that it needs to be in when you go into the ice table to do that calculation. We could solve it a couple different ways. We saw one way, obviously, is our quadratic, right? So ax squared plus bx plus c equals 0, where x is equal to minus b plus or minus square root b squared minus 4ac divided by 2a. Remember that this will give you 2 answers, and again, one will not make sense. And typically how it will not make sense is when you go back into the equilibrium line with one of the values you'll end up with like a negative value. So obviously you can't have a negative concentration or pressure. So obviously that is the one that you would not want. And obviously the one that gives you a positive value is the one that you want. Now, also remember that you can get two positive numbers off of that. You can get a positive and negative, and you could get two negative numbers. And, again, you really want to look at sort of whichever one, when you go back into the equilibrium line, works out to all positive sort of numbers. We also had like a perfect square as well. We had one that we did. Again, you could also look at that type of way of solving it as well. Any questions on that so far? All right, let's try another one here. I think where we left off, wherever it's at, there it is. All right, so KP is 4.31 times 10 to minus 4. You got your calculate the equilibrium pressures of everybody if it is 0.862 atmospheres of N2, 0.373 atmospheres of H2, according to that equation. Again, as I mentioned a second ago, pretty much work it the same way as long as they are, even if they are pressures. Give it a go, see what you come up with in this case. Yeah, let's take a look, see how you're doing. So here again, we do have pressures, and we do have a KP value, which makes sense as we have pressures. So it all works the same. We can still do an ice table. As I mentioned before, you definitely want to make sure usually that those pressures are in atmospheres, which they are in this case. So again, we're good really just to sort of proceed like normal, except obviously here we'd be looking at a KP expression, which would be the partial pressure squared of NH3 divided by the partial pressure of N2 and the partial pressure of H2 cubed. And again, that would equal our KP value in this case. So pretty much everything works kind of the same. So I'll just go here and borrow that there. So initially here we have 0.862 and we have 0.373. Nothing given to us in terms of our product, so we could assume 0. Again, let me write my KP here, pressure, NH3 squared, and a partial pressure of N2, partial pressure of H2 cubed, 4.31 times 10 to the negative 4. Okay, change here going to be minus x. Again, we could assume safely that it is heading in this direction since we have no products. Minus 3x, once again, for the coefficients. We got to take those into account. We should be adding some products here, so a plus 2x on the product side. Bringing everybody down here, 0.862 minus x, 0.373 minus 3x, and 2x. Any questions on the ice table here? All right, so like normal, we're basically going to take our equilibrium line and we're going to put it into our expression here, and that is going to give me 2x squared up on top, products over reactants here, 0.862 minus x, and 0.373 minus 3x cubed is going to equal 4.31 times 10 to the minus 4 in terms of our KP value in this particular case. At this point, we need to do some math, and that looks like some scary math, so we probably should just go to the next problem, I imagine, and not do any of that, I suppose. But we actually can sort of maybe get around some of the scary math of it, which is we can look at our K value here, right? And when I look at my K value, this value here, is it a large value or a small value? It is a small value, right? And because it is a small value, and when we have a small value of K, that means when I reach equilibrium, would I mainly have reactants or products here? You have a small value K, you mainly have 50-50 shot there, reactants, products. You would have reactants, right? Since it's products over reactants, small value K means that you should mainly have products, our reactants, which are not products, but mainly have reactants there. And because you'll mainly have reactants when you reach equilibrium, that means that when we think about the change part here, as it is changing, and really our X part here, the change, that change should be relatively small. So in a situation like this where you have a small K value, because you'll mainly have reactants at equilibrium and because the actual change part should be relatively small, you can make an assumption and you could assume that X is equal to 0. And again, X being our change is going to be relatively small here, negligible, if you will. It's going to be on the small side. Now, does that mean we get rid of all the X's? The answer is no, because frankly, you have nothing to solve for, so you can't get rid of all the X's. So when we talk about X is equal to 0, we're talking about any X's that are going to be subtracted from a number or in some cases added to a number. And that's going to be what we're going to basically zero out here. We really can't zero out this guy other than the fact that you can have nothing to solve for. But if you just think about it logically, that guy started at 0, which means whatever it gains is pretty significant from where it started, right? So it started at with nothing. So any little bit that it might gain is still going to be relatively significant. The other guys, we already have starting amounts, so whatever they lose might be relatively not as significant. So with that being said, what that's going to do is turn this into 2x squared. We're going to have 0.862 times 0.373 cubed equals 4.31 times 10 to the minus 4. That looks like a lot easier a move in terms of solving. So if we do that, we're going to maybe clean up the bottom side there, and we got up on top 4x squared. We have basically 0.373 cubed times 0.862. That's going to give us something like 0.044733591 equals 4.31 times 10 to the minus 4. At this point, we're going to multiply that to the other side. That will give me 4x squared is equal to 0.00001928. Obviously, I'm going to divide by 4, and then I'm going to square root it. So I'm going to divide by 4 and then take the square root. And that's going to give me an X value here, I believe, of 0.002. We'll call it 220 there in that case. Any question on that move there? Now, if you choose to make an assumption like we just did in this problem to make the math perhaps a little bit easier, we do have to check our assumption. So whenever you make an assumption, you do have to check it. So the way that we're going to check our assumption is we're going to use what is referred to sometimes as the 5% rule. And basically, the way that you check your assumption is you take the X value that you just got and you basically divide it by whatever you're going to like subtract it from or add it to. So for example, here we could check it by taking 0.00220, which is the X value we got. We could divide it by 0.862 times it by 100%. And if we do that there, divided by, 0.00220 divided by 0.862 times 100, that's going to give us a 0.255%. That is less than, obviously, 5%, which means this check is good as long as it's less than 5%. You could actually do it with really either one. In my experience, if, for example, the first one works to check, you don't really have to check everybody. Usually they'll be good for everybody. But if you're going to do it for the other one, you would actually take 3 times the 0.00220 and divide it by 0.373, times it by 100%. And you got like a 1.77%, also less than 5. So the check is good in both cases. Again, you don't usually have to check them all. If you check one, usually you're pretty good shape for everybody else that's there. Now, what this means is if it is above 5%, that is too big of a percentage to do the assumption. And what that would mean is you would have to go back and solve it some other way, be it a quadratic formula or something like that. You would have to kind of go back and do that. Any questions on that there? We're able to do that. It's really because of the K value, and the K value is a small value, which means that when this thing reaches equilibrium, you should mainly have reactants. And because you should mainly still have reactants when it reaches equilibrium, that means there has not been a lot of change that has occurred from the reactant side to the product side. And that means that the X, which is the change, should be relatively small, almost negligible. And that's why you could kind of zero it out. That is also why did we not use this, say, on our previous examples where we had K values of, I think, 7 and 54.3, right? Why did we not use it on these ones? The K values here are large, which means when we reach equilibrium, we should have mainly products. And that means that the change is going to be relatively big. That's going to happen right from reactants to products here. So it is the K value that determines whether or not you're allowed to sort of use the assumption or can use the assumption to solve the problem. And it needs to be a small value. The assumption will not always work, just so you know. It is kind of dependent on sort of the initial concentrations of everybody. So just so you know, the assumption may not always work. If you have a relatively good sort of initial concentration, probably your assumption will be good. If you are starting with a relatively small values in the initial concentrations, it may not work. And you could think of it like a pizza, right? If you have a whole pizza and you take one slice out, right? It's not a very big percentage of what you lost. But if you have just like 2 slices left, right, and you take out one, that's a much bigger percentage. So if you have a much smaller concentration to begin with, even though the change may be relatively small, it's going to be a bigger percentage of what you started with than, say, if the concentration was larger and the change is small, it's going to be a smaller percentage of what you start with. Any questions on that there? Yeah. Yeah, so pretty much any K value that is technically less than 1 is considered small, and you could try the assumption. Now, if you don't want to worry about doing the assumption and you like to do quadratics in the long math, you absolutely could still roll with the long math. You don't have to do the assumption. You could solve it mathematically, you know, kind of like what we did previously as well. Other questions? So speaking of that, we should probably solve this. So let's actually put those guys back in here. So maybe I'll just erase around here. Pop it in here. All right, so now that we checked our assumption is good, we don't have to go back and solve it some other way. That is going to be our X value. That means that the partial pressure of N2 in this case would be 0.862 minus our X value of 0.00220. And that is going to get us there 0.00220. Something like 0.860 atmospheres. Remember, it does need units as they are pressures. Partial pressure of H2 would be 0.373 minus 3 times 0.00220. And that's going to get us here. .366 atmospheres. And lastly, our partial pressure of NH3 equals 2 times X, so 2 times 0.00220. Gonna get us there 2 times 0.00220. 0.00440 atmospheres in this particular case. Any questions on that there? Again, you can, as we've talked about previously, double check yourself if you like at the end. You can again take those equilibrium pressures and put it back into there, and obviously you should get a K value close to what we got there. And I think if you do that, you get something like 4.6 times 10 to minus 4, which is fairly close in terms of how close we are. You could also see that the change wasn't very big, right? This guy started at 0.862, ended at 0.86. This guy started at 0.373, ended at 0.366. So again, our assumption is sort of valid, as there wasn't a very big change in terms of the pressures as we go from reactants to products. Any questions on that there? So we've now seen a few different ways to solve these equilibrium problems. Again, you could use the quadratic formula. You could have a perfect square situation. You could do the assumption. And again, those will be pretty much the three ways that we will solve these problems in this class. As I mentioned before, there's a third or fourth way, I guess, which is known as successive approximation, which, as we know, for example, you know that this value has to be less than this value. So you basically would put an x value less than there into this equation, and you would keep kind of putting it in until the number that you put in and you get out are the same. So for example, I erased it, but our K expression was 2x squared over 0.862 minus x, 0.373 minus 3x. So what you do in successive approximation is you put that x value into these two spots and you would solve for this x value. And every time you put a number in and solve for x, you keep going until the number you put in and the number you solve for are basically the same, which could take you all day if you're really crappy at it. And so we will not be solving the problems that way. But you may see it in books and stuff like that. Sometimes it's how they solve some of these problems. There's no successive approximation. And again, the idea is until you put the number in and get the same number out, that is sort of the answer. So again, we will stick to perfect square, quadratic, and you can make an assumption as the way we solve it. Any questions on how to solve these type of problems? Okay. Last thing we're talking about in this chapter is our friend Le Chatelier's principle. And Le Chatelier's principle is this idea of you essentially have a system that's at equilibrium. So you got this system that's at equilibrium, which, as we've talked about, means that basically our rate of the forward direction will equal the rate of the reverse direction. So essentially what happens at that point is everybody, as we talked about, gets locked into place. So as they go back and forth at the same rate, everybody is able to maintain their concentrations. They're able to maintain their pressures because, again, they're going back and forth at the same rate. So the idea of Le Chatelier's principle is you have the system at equilibrium, and frankly, you do something to it to screw up the equilibrium. So you add some type of stress to the system that is at equilibrium. And what that's going to do in a lot of cases is, frankly, mess up the equilibrium. So you're going to mess up that rate of it going back and forth at the same rate. Some stresses that you can sort of add to a system at equilibrium, you could do something with concentration. And obviously you could either add more or remove, are very common type of things that you can do. You could also do something with the pressure and volume. Pressure or volume or both. You could also do something with temperature. You could obviously either increase or decrease the temperature. And lastly, you could add a catalyst, as we talked about in the previous chapter, which speeds up a chemical reaction to it. So these are all things that will, in a lot of cases, really mess up the equilibrium. And what's going to happen when you do something to a system that's at equilibrium is it can sort of, in most cases, what it wants to do is sort of right the ship, and it can fix itself basically. And it can kind of fix itself because it is a reversible reaction. So if you do something to it, it may fix itself by shifting to the right, which means you're going to make more products. It may need to fix itself by shifting to the left, which means you need to make more reactants. Or believe it or not, there is certain situations that even though you did something to the system, it will actually have kind of no change or no effect sort of on it, even though you kind of did something to it. So there is sort of a no change option that can also occur. So those are sort of the three basic sort of answers for Le Chatelier's principal question. You know, it really asks sort of which way is going to shift if you do this to the equilibrium. So because you messed up the equilibrium, this reaction itself wants to get back to that equilibrium state. And again, that is the one of the three ways that it's going to be able to sort of right the ship, if you will, and sort of correct itself. So let's talk about each of these and sort of what happens. We're going to start with concentration here. So obviously, as I mentioned before, you can either add more. And when you add more concentration, it will have itself shift away from the side you added it to. So a good way to remember that is AA, add away. Yeah. So whatever side you add it to, it will shift away. That means if you add reactants, it will shift towards the product side. If you add products, it will shift towards the reactant side of the equation. So when we talk about, by the way, kind of shifting to the left, shifting to the right, we are talking about really the equation, if you will, right? So when we talk about it shift to the right, shift to the left, we're talking about, you know, the equation as it's written. Clearly, when you put something into a beaker, there is no really right or left side, right? There is really everybody just floating around basically in the beaker. So when we refer to sort of right or left, we are basically referring to sort of the equation as to will you be making more products? Will you be making more reactants? Now, if you remove something, it will shift away. I'm sorry, it will shift towards. So if you remove, it will shift towards the side you removed. So if you remove reactants, it will go towards reactants. If you remove products, it will go towards products. Adding is pretty simple to figure out. If you wanted to add something, you just go grab it off the shelf, whatever it's there, and drop it in, right? Drop some solution that has the ions, for example, that's in the equation. Could be reactants, could be products. You just kind of drop it into the solution, right? Now, if I have a solution in a broken beaker, apparently, there we go. If I have a solution like that and I want to remove something, do I just reach in and grab my hand, pull it out? That's probably not a good idea, right? By the way, in most cases, what is really in there that's going to affect equilibrium? It is ions, right? And ions are found floating around in the solution, basically, right? That's basically what it is. When we look at the equilibrium expression, right, we include only things that are aqueous, right, which are ions floating around the solution, and gas molecules, which are flying around, basically, right? So if I wanted to remove something, how can I remove something? What are one of the things that we do not include in the equilibrium expression? Things that are solid, yeah. So things that are solid. So one way that you can remove something is you could add something else to it that maybe will precipitate out something as a solid, right? And that is effectively reaching in there and pulling out that ion from solution. It's no longer floating around in the solution. It reacts with something that you put in there, makes a solid, right? Drops to the bottom. Probably not. If you centrifuge it, it'll drop to the bottom. But you'll have this solid that's made. And that's essentially like reaching in there and basically pulling out those ions. So that's a very common way that we could remove something from an equilibrium, is to add something else that will react with some ions that are floating around, make it precipitate, and that will pull it out. Another way that you can remove something from an equilibrium solution, for example, what is the other thing that we don't include besides solids? Liquids. Yes, pure liquids like Water, yeah. So if you have some type of equilibrium where maybe you have hydroxide floating around, right? And I add an acid, which is an H plus. H plus OH minus will make water. And that will be essentially like removing hydroxide from that solution. Obviously, if you had H plus in there, you could add hydroxide and do the same thing. Will you see the water? The answer is no, you can't see water pretty much, right? It just looks like everything else that's floating around in there. You won't be able to actually see it happening, but that is essentially what is happening to cause either hydroxide or H plus to be removed. The precipitate, clearly, if you did that, you would be able to see the precipitate being made in the beaker or whatever it is, and you'd be able to see the solid form. So those are two very common ways that you could kind of remove something from an equilibrium solution, either precipitate out some ions or add an acid or a base to make water, which will remove hydroxide or H plus ions that are in solution. So to illustrate sort of this point here, let me do some award-winning drawing here. So let's just say we had a system at equilibrium. This is advanced stick figures because they do have faces, just so you know. We'll call this guy our reactant side. They'll call this guy our product side. And we'll just say that they are at equilibrium here. Equilibrium position number one. So let's just say, for example, that somebody decides, hey, let's hop on this side over here. What's going to happen in this case is this situation. Right. To fix this situation, I need more people on the right or more people on the left? More people on the left. It needs to shift away from the side that we added, right? And you put more people there on the left to have it once again come back to equilibrium position here. Back to equilibrium. So we added more products in this case. We have to make more reactants to reach equilibrium. Same idea if we did something like this here and we had the same situation. So starting here at equilibrium, put both guys up there. Now let's just say that this guy decided I had enough. I'm going to hop off. So he hops off. This is going to happen. This guy's going to crash to the ground. Not very happy. And in this situation, we would need more people on the left or right to fix it. We need people on the right, right? So we'll shift towards the side we removed it from, and we will once again get back to equilibrium. Any questions on that there? Why is this really happening? Well, if we think about the wonderful drawing here on the left where we add in more products, right? And we think about the reaction of reactants going to products. When we add more products, that means that we have a lot more products available to react than reactants in this case. And that should kick off the forward or reverse reaction. Should kick off the reverse reaction, right? Which means it's going to shift away from that side and it's going to cause that reverse reaction to occur. When we look on the one on the right, we remove products, which means in that case, we now actually have more reactants available. And that's going to cause the forward reaction to occur, right? And head towards the side that we actually removed it from. So what's really happening here is just the availability of reactants versus products causing either the forward reaction or the reverse reaction to really kick into play. And that's what causes it to shift towards or away from what we did there. Any questions on that there? All right, so that is concentration. Let's talk about then pressure and volume. They are oftentimes tied together. There is a relationship with pressure and volume that you remember from Chem 50. Our friend Boyle, what is that relationship? As pressure goes up, what happens to volume? Not everybody at once. It goes, again, 50-50 shot here, up or down. It does go down. Yeah, one goes up, one goes down, right? And that is because in a very small volume, you have all your gas molecules together, right? A lot of collisions in that very small spot, not a lot of room to fly around, causes a lot of collisions, a lot more pressure. And obviously, as the pressure goes down, the volume goes up. So in this situation, when we're talking about pressure and volume, a lot of times we're talking about gas molecules here in the equilibrium. And if you have a situation where your pressure has gone up, and that is a result of your volume going down. So really the change that we're seeing here is the pressure is starting to go up. We actually want to bring the pressure back down. But the problem is my volume now is really small. What is a way to bring the pressure back down in a small volume? Would I need more gas molecules in that small volume or less gas molecules to bring the pressure down? Less, right? So small area, less gas molecules. So what's going to happen in this case is it will shift to the side with the least number of gas molecules. And that obviously is dependent on the equation you're looking as to which side is the least. You would obviously look at anybody that has a G next to it, right? That's a gas, and look at the coefficients and add them up on both sides of the arrow, and that will tell you. Opposite is true. If your pressure goes down, your volume goes up. The change that occurs, your pressure is dropping because your volume is now larger. So in that larger volume, you need more gas molecules to fill it to bring the pressure back up. So it will shift to the side, bless you, with more gas molecules. And again, that is dependent on the equation that you're looking at. What happens if I have equal gas molecules on both sides? Which way will it go? The answer is nowhere, because there is no greater or less gas molecules. So you could have a tie, and that's one way you could get like a no change to occur. If you have this type of situation, you got equal number of gas molecules on both sides, it's going to be a tie. It will not go one way or the other, and you'll have no change that could occur. Question on that there. So if we had something like, say, this plus so what I want to know is, will it shift to the right, to the left, or no change if I do the following things? I increase the volume, I add more C, I remove B, I increase the pressure, I add more A. All right, so take a moment for each of those. Which way will the equilibrium shift? We're going to increase the volume. So again, that's really going to decrease the pressure. But really, if you think about it in terms of volume, larger volume needs more gas molecules. So left-hand side, I got 2 and 3 is 5 gas molecules. I got 4 here. So in this case, it should shift to the left-hand side, which is more gas molecules in this particular case. Any questions on that one there? I'm going to add more C in this case. C is a product, which means I have now more products than, say, reactants. That should kick off the reverse reaction to occur. And that should cause it to shift away from the side we added it to and basically head towards our reactant side. If I remove B, essentially what that will mean is, again, I will actually have more products as I got rid of some reactants. That also will cause more products to collide and start reacting and cause the reverse reaction to occur and go towards the side I removed it from. So it should go to the left. Any question on those there? We're going to increase the pressure. So when we increase the pressure, our volume is going to get smaller. So once again, think about it in terms of volume, small volume, less gas molecules, larger volume, more gas molecules. So small volume here, we need less gas molecules. which we already determined is to the right in this case. And lastly, here we're going to add more A, which is over here. Adding more A will again make the reactants more available to each other, and that really will kick off the forward direction and cause it to shift away from where we added and go to the right. Any questions on any of those things? By the way, when you play with equilibrium reactions, you could screw up the equilibrium, bring it back, go back and forth all day. You can play with it, make it go one way, make it go the other way, and it'll just keep going back and forth in a lot of cases. All right, so that's pressure, volume. The next thing that could affect sort of a system at equilibrium is our friend temperature. Yeah. So temperature works the same as concentration. So when you increase the temperature, it will shift away. And when you decrease the temperature, it will shift towards it. The problem is we need to know which way is away and which way is towards it. And where this comes into play is actually the type of reaction that you're dealing with in terms of energy. So we have exothermic reactions where heat and energy is released. And in those type of reactions, we consider heat and energy to be a product. So we consider it to be a product, which means if you have an exothermic reaction and you increase the temperature, it will shift away. So it will shift to the left in this case. And if you have an exothermic reaction and you decrease the temperature, you put everybody on ice, all your test tubes on ice, it will go towards the product side in this case, as heat is considered not perfect in all aspects of it, but considered basically a product. An endothermic reaction is the opposite. Endothermic, we have heat and energy absorbed. And it is considered a reactant in that situation. Which means you have the opposite effect, that if you have an endothermic reaction and you increase the temperature, it will actually shift to the right away from it and make more products. And if you have an endothermic reaction and you lower the temperature, it will shift to the left towards the reactant side. Most likely, in most cases, the way that we determine exothermic and endothermic is they do not write heat or energy a lot of times in the actual equation. We look at the delta H value for these things. And if I have an exothermic reaction, the delta H value should be positive or negative? Should be negative, yes. And if I have an endothermic, it should be positive. And that's most likely how you'll be given that information, these type of problems. They'll give you the equation, and at the end, they'll go, the delta H value is negative 300 kilojoules. And the number doesn't really matter. It's really the sign at that point for Le Chatelier's principle. Is it a positive or negative value for delta H, which will tell you if it's exothermic or endothermic. Any question on temperature there? All right, the last thing that you could kind of do to a system is add a catalyst, which, as we've talked about before, is not a reactant. It's not a product, and it does not get used up. In the reaction. It is there in most cases just to speed up that reaction. And as we talked about in the previous chapter, it does so by finding a more efficient pathway, and it ultimately will lower the activation energy to allow the reaction to occur quicker. In the case of Le Chatelier's principle, it will actually cause a no change, basically. You'll just get there quicker, but it will not cause any type of change to occur. And that's another way that you can kind of get to a no change. So you could have kind of equal numbers of gas molecules. You could also have like a catalyst added. You could also, for example, in some cases, add a noble gas. Noble gases are chemically inert. They don't react. That also is another way that, you could kind of get a no change situation to occur. Any questions on those there? All right, so let's take a look at some more examples here. I'm just going to steal some of these equations, maybe that we talked about. By the way, speaking of temperature, that is, as we talked about a number of times up to this point, really the only thing that will affect the value of the rate constant. But again, in this aspect, we're just looking at what it will do there. All right, let's do this one, and let's just say that we'll just pretend that this is not this value, so at all, but we'll just do this. All right, just say we have this. We want to know again what's going to happen here. We're going to shift to the left, shift to the right, or no change. If we do the following, let's decrease the pressure. Let's add some N2, which lower the volume. Let's increase the temperature. Let's add a catalyst. Let's remove NH3. All right, so see what happens in each of these cases. The first one, we're going to lower the pressure. If we lower the pressure, that means that we actually should have a larger volume, right? In that case. So larger volume means we need more gas molecules. And in this case, we have 4 here. We add up the coefficients for anybody with a G. And here we have 2. So that means in this case, we will shift to the left, which has more gas molecules in this case. Any questions on that one there? Adding more N2. N2's over here on our reactant side. That means we're going to have really more reactants and products. That should kick off the forward direction and move away from the side we added it to and go to the right. If we lower the volume, we would see an increase in pressure, but in that lower volume, we would need less gas molecules. Again, because our pressure is going up, we want to bring it back down. We would need less gas molecules, so it would also shift here to the right. Any questions on those 3 there? I increase the temperature here, so that is where my delta H value is going to come into play, and really not the value, but really the sign here. That sign is negative, means this reaction is endothermic or exothermic. It is exothermic, right? Because of the sign. That means that we can consider in this application heat as being a product, like it's being given off. And that means that if we increase it, it would be like increasing the products, which should kick off the reverse reaction to occur. And it should go away from the side we increased it from and should shift to the left in this case. Any questions on that there? Adding a catalyst will cause no change to occur, basically. Lastly, we're going to remove NH3, which is over here on our product side. When we remove NH3, we are essentially having now more reactants than products. And because of that, that will cause the reactants to start colliding and reacting and cause the forward direction to occur and cause it to shift towards the side we removed it from. Any questions on any of those there? Look at one more here. I think that's what I just did. This one, perfect. All right, so let us do this one here, and let us add N2, decrease temperature, increase volume, remove O2. Add NO. Increase the pressure and increase the temperature. All right, same idea. Left, right, no change in this situation. Some N2, which is a reactant, that's going to cause, again, more reactants to start to react and will cause really the forward direction to occur, and will shift away from the side we added it to. We're going to decrease the temperature here. This one is endothermic, which means if we had to put sort of heat or energy into the equation, it would be considered a reactant, as the delta H here would be a positive number. And because of that, we're going to decrease the temperature. That would be like removing reactants. That would mean that we would have more products and reactants, and would cause actually the reverse reaction to occur and head towards it, basically where we removed it from. Question on that one there. Increasing the volume here will decrease the pressure, but increasing the volume means that we would need more gas molecules to sort of fix the decrease in pressure. Here on the left-hand side, that is 2 gas molecules. On the right-hand side, that is also 2 gas molecules. That means in this case, it would actually be a no change, right? There is no kind of more or less gas molecules, so that'll be kind of like a push and no change. If we remove O2 here, that is a reactant, so it'd be like removing our reactant side, and that would mean we have more products, so that will cause the reverse reaction to occur, and it goes towards the side we removed it from. We're going to add NO. Adding NO, which is a product, would cause, again, more products to react, causing the reverse reaction and it's shifting away from it. Increasing the pressure means that my volume has gone down, and as we just saw a second ago, that is going to be a no change as well, as there is no kind of greater or smaller side. Normally, to see a change, we would need, in this case, less gas molecules, which we obviously don't have. Lastly, increasing the temperature means in this last case, we would be increasing our reactant, and that will cause more reactants to react and the forward reaction to occur, and it will shift away. Any questions on any of that there? Questions on Le Chatelier's principle, equilibrium, chapter 13, exam 1 week from today, quiz on Thursday on chapter 13 to warm you up, yes. So we'll take a quiz on 13 all the way through everything but Le Chatelier's principle. So we'll do everything but Le Chatelier's principle. So equilibrium problems, Q, and just basic expressions and all that. Warm you up for next week. Yes? Any questions on that there? All right, then we're gonna go off to chapter 14, which would then be exam 2 material, also known as the hardest exam of the season. Yes, so this starts the hardest material. We're going up the hill of hardness before we drop back down, hopefully, after chapter 15. Chapter 14 is the longest chapter forever, so probably about 4 weeks from now, I'll be going, oh, we're still on chapter 14. We're almost there. So in a lot of books, they break up chapter 14 to 2 separate chapters, but this book just rolls with it in one ginormous chapter. So there's a lot of material here. The first part here is kind of maybe some stuff that you maybe have seen before. We're going to talk about acid bases. We're going to talk about pH and all that. And then towards the second half of sort of chapter 14, we will get into some equilibrium calculations involving acids and bases and acid-base sort of equilibrium chemistry. So we'll start with the opening part here, which is acid and bases, as my acid is hiding behind my orange, it looks like back there. So that is my acid, I think. There you go. So an acid has a sour taste. Obviously, don't teach any acids or bases in lab. But vinegar, major component of vinegar is acetic acid, which is a weak acid, citric acid, and fruits. Acids tend to react with metals to produce hydrogen gas in a reaction that you're probably familiar with, perhaps. Say we take a little bit of this here, a little single replacement reaction, right? Knocking out the hydrogen, making a little zinc chloride action and a little hydrogen gas. I'll balance it like I'm a chemistry person here. There we go. So a little single replacement reaction. By the way, for this reaction to take place, the guy coming in needs to be more or less reactive. Doesn't be more reactive or it doesn't occur, right? They also react with carbonates and bicarbonates to produce carbon dioxide gas. You know, if you took something like this, then a little bit of, say, sodium carbonate or bicarbonate will make a little bit of NaCl plus carbonic acid, H2CO3. That H2CO3 will quickly go through a decomposition reaction where it will produce H2O and CO2 gas, right? And plop, plop, fizz, fizz, a little balancing there as well as we go through it. Now, speaking of acids, just to make sure everybody's on the same page, we'll back up here. Acid naming, right? As you hopefully remember, all involves whether or not there is oxygen in the acid, right? So if there is no oxygen, that is something. No, it is not. So it is it is an eraser. I'll try that again. There we go. So that is hydro something-ic acid. So HCl in the aqueous there is hydrochloric, right? Acid. HBr is hydrobromic acid, right? The cation for every acid is H plus, right? Is the cation. The anion is whatever it's attached to. We typically put aqueous next to acids because they are in solution, and that's what makes them acid, is that right there, the ability to release one of those H pluses. That's also why HCl in the gas phase is called hydrogen chloride gas, right? Not hydrochloric acid. So that AQ is typically written next to acid formulas. If your acid does have oxygen, right, it will contain everybody's favorite thing, a polyatomic ion. Ugh. Polyatomic ion ends in either ate or ite, right? So if your polyatomic ion ends in ate, your acid will be something-ic acid, like HNO3. That is nitrate. This is nitric acid, right? H2SO4. SO4 is sulfate. That is sulfuric acid, right? If your guy does contain oxygen and your polyatomic ion ends in ite, your acid would be something OUS acid. So like HNO2. That is nitrite. That would be nitrous acid, right? H2SO3. SO3 is sulfite. That will be sulfurous acid, right? Any questions on acids? How to name them, right? That way you don't go like that thing over there, that acid over there. So make sure you know how to do that. All right, so back to that. Bases, on the other hand, are things that do feel very slippery. Many soaps contain bases. Things like Drano and that type of stuff, those are all bases. You can go to Home Depot and buy like straight sodium hydroxide and to clear your drains. Comes with a lot of warnings. A lot of bases contain hydroxide in them. A lot of strong bases come from group 1 and group 2 on the periodic table. Group 1 and group 2, that's the alkali metals. All right. Group 2, the alkaline earth metals. The word alkaline means basic. So a lot of guys in group 1 and group 2, you throw a little hydroxide, OH on them, OH minus, like lithium hydroxide, sodium hydroxide, potassium hydroxide, hang right there at calcium, strontium, barium. Those are all strong bases in those cases as well. Now, a early sort of definition of an acid and a base is the Arrhenius sort of definition. And an acid is something that produces H plus ions in solution. H plus is the hydrogen ion. In chemistry, especially when you're dealing with acid and bases, H3O plus, which is the hydronium ion. They are essentially equivalent to each other. They mean the same thing. They mean the acid part. So H plus, H3O plus will be used interchangeable, both in equations and also formulas as well. I personally roll with H plus most of the time, but a lot of books and stuff now use a lot of times H3O plus. So wherever I put H plus, you could kind of put H3O plus in this place. It's basically the same thing. H plus is also known as a proton, right? And that's because hydrogen has one proton, one electron. How many neutrons? 0. So in order to become positively charged, it had to lose an electron, which leaves it just a proton. So very commonly in acid-base chemistry, H plus is referred to as a proton as well because of that. So an acid is anything that has the ability to produce free H plus ions in solution. That means the ability to produce in that beaker of solution free H plus ions floating around, not attached to anything, just freely kind of floating around. A base, on the other hand, is something that has the ability to produce hydroxide, OH minus ions in solution. Same idea, has the ability to drop out some OH minus in solution. Why in certain cases do we see perhaps H plus versus H3O plus? It has to do with how you write your equation for the acid, for example. So if we take hydrochloric acid here, this is basically just hydrochloric acid dissolved in water. So in this equation, they actually included the water in the equation, and they will get H3O plus. You can actually write the same dissociation of this acid which is a strong acid, by just taking HCl and breaking it apart into H plus and Cl minus. These are two equivalent equations, except that in the second one, I did not include the water. So I got just H plus. And in the top one, they did include the water. So that's just how they get H3O plus. So it has to do with sort of this water as being included in the equation. And that's how they kind of produce that H3O plus. Now, as I mentioned before, a lot of strong bases come from group 1 and 2 on the periodic table. Again, kind of like sodium, potassium, hang over there to calcium, strontium, and barium, all with hydroxide. But not all bases will actually have hydroxide in their formula. Something like ammonia here, which is NH3, that is actually a weak base, and we'll talk about that in a bit. And although it does not have hydroxide in its actual formula, is able to do a little reaction actually with the water, and it's able to produce hydroxide. And because it's able to produce hydroxide in solution, it is considered a base, but it's a weak base. So there are weak bases, there are strong bases that we'll talk about, there are weak acids and strong acids that we will talk about as well. But what makes an acid pretty much an acid is that ability to produce free H plus in solution. What makes a base is the ability to produce hydroxide. Now, a more general definition of an acid and a base is the Bronsted, I really should add his name back in, Lowry. So this is the Bronsted Lowry definition. The Bronsted Lowry definition of an acid is a proton donor. A proton donor, again, is an H+, and a Bronsted Lowry base is a proton acceptor, so something that will accept an H+. It's really important to understand that it is not just a hydrogen being exchanged, but also the plus part of it, because that affects the overall charge. If somebody loses an H+, they will lose a hydrogen, but they will also lose the plus part, proton, basically. So if you lose a proton, you become one more negative, right? Because now you got more electrons than protons, basically. And when you gain an H+, you will gain the hydrogen and that plus, which is really the proton. You will actually have more protons than you had to begin with, and you'll become more positive. So very common when people sort of think about losing and gaining that H+, they oftentimes will not get the charge correct because they just think about the H part and not the plus part of it. With that being said, in this particular case, what is happening is the water will actually be sending an H+ over to the NH3 in this case. And what that means is, in this example, the water is acting as the Bronsted Lowry acid as it is donating the proton over. The NH3 will accept the proton, which means it's going to act as the Bronsted Lowry base in this case, as it accepts the H+. The consequence of the Bronsted Lowry definition of acid and bases is it will actually create some partners to those acid and bases on the other side of the equation. So if we look at this guy here and this guy are related to each other. And the NH3 on the left-hand side is the base. On the right-hand side, what it becomes is known as the conjugate acid. And the water on the left-hand side, which is the acid, is related to the OH minus on the right-hand side. And that is what is known as the conjugate base. So we create these partners on the left-hand side and right-hand side of the arrow that are related to each other by a really important difference, and it is this guy right here. Only one H+ difference between your base and its conjugate acid and your acid and its conjugate base. The base has one more H+ than it started with. The conjugate base has one less H+ as it goes to the other side, as it did that. That is the only difference there can be when you're comparing Bronsted Lowry acid and conjugate bases and bases and conjugate acids. The only difference between them can be that H+ difference. Any questions on that?